first video for section 3.7 in AP Calculus on implicit differentiation. So to begin with, we are going to find the derivative for this equation the way we've been doing it. So example 1 here says to find dy dx given x squared plus y squared equals 4 by solving for, that should say by solving for y, and then finding y prime. So what that means is if I was to try to find the derivative, to find dy dx for this equation, using all the tools that we know up until this point, then I'm used to having my equation written in y equals 4, which would mean that I would have to take x squared plus y squared equals 4 and first solve it to put it into y equals 4 before finding the derivative. So I would subtract the x squared, and then I would take the square root, but when I do that, I would get both a positive and a negative square root of 4 minus x squared, which means I now have 2 equations to find the derivative of. So if I have y equals the positive square root of 4 minus x squared, that plus y equals 4 minus x squared to the 1/2 power, dy dx in that form, we would do the chain rule, so we would have 1/2 times the derivative of the inside with our new exponent of negative 1/2, and then times the derivative of the inside, which would be negative 2x. So put all that together, the 1/2 and the negative 2x could multiply together to give you an x. And then this negative 1/2 power would mean that we could make it positive by putting it in the denominator, and we could take it back to square root form. So that would be the derivative of the positive square root of 4 minus x squared. But what if we use the negative square root of 4 minus x squared, or negative 4 minus x squared to the 1/2 power? That derivative, dy dx, we would have the negative, we bring the 1/2 in front. Our new exponent is negative 1/2, and then using the chain rule, the derivative of the inside would be negative 2x. So that would give us negative 1/2 times negative 2x would give us a positive x over the square root of 4 minus x squared. Notice that did not, or it did give us the same answer as the positive square root of 4 minus x squared. Actually, this up here should have been negative. We had a positive 1/2 and a negative 2. So we did get 2 different answers there because we had 2 different equations that we were taking the derivative of. And that also took me twice as long to find the derivative because I had to solve for y, and then I had 2 equations, but I had to take the derivatives of the 2 equations. So wouldn't it be great if there was a way that I could have taken the derivative of x squared plus y squared equals 4 back at the beginning of the problem without having to do all the solving for y and getting 2 equations and doing 2 derivatives and all of that. So that is where implicit differentiation comes in. So the implicit differentiation process is to differentiate both sides of the equation with respect to x. So that means that every single term of both sides of the equation are going to be differentiated with respect to x. So even the things that have y variables in them are going to be differentiated with respect to x, and I'll show you in a minute how to do that. Then you'll collect the like terms that have dy dx's in them on one side of the equation, factor the dy dx out of those terms, and then solve for dy dx. It really is a relatively simplistic process. So we are going to go back and look at the exact same problem again, but not solve for y to begin with. So we literally just go term by term through here. So I start with the x squared. The derivative of x squared is 2x. I just took a derivative of an x variable, so I'm good to go. Then I bring down my plus sign. The derivative of y squared, that's also a power rule problem, so that would become 2y. The problem is I just did a derivative of a y variable, but my directions are to differentiate with respect to x. So what you do is for any term where you took a derivative of a y variable, you write dy dx next to it. That's how you convert, essentially, from a derivative in terms of y into a derivative in terms of x. So the derivative of y squared would be 2y dy dx. Then you bring down your equal sign, and then the derivative of 4 is 0. Now, we are trying to find dy dx. So these implicit differentiation problems are not going to be done until they say dy dx equals. So at this point, the derivative is taken care of. It's now just an algebra problem of solving for dy dx. In this particular problem, I only have one dy dx, so I just need to isolate it. So we could subtract the dx to the other side, and then we could divide by 2y. And so when you simplify that, you end up with dy dx equals negative x over y. Yeah, we've got the same derivative as we got back in example 1 with the exact same equation, simply solving for y first. Well, if we go back and we look at example 1, our answers were negative x over the square root of 4 minus x squared and positive x over the square root of 4 minus x squared. Remember though, the square root of 4 minus x squared was y. So this really is negative x over y. And then the same thing down here. X, and then the square root of 4 minus x squared, well, the negative of it would be y. So the positive of it would be negative y. So even though we didn't realize it in example 1, we really did find negative x over y. It is perfectly acceptable, though, to write dy dx as negative x over y in terms of both x and y variables there. So we can use implicit differentiation to do things with functions and equations, just like we have been using trig derivatives and the chain rule and product rule and quotient rule and all the other derivative rules that we've learned up to this point. For example, we're using what we got back there in example 2 with x squared plus y squared equals 4 to find these various things. So part A just wants dy dx for the point 1 comma square root of 3. So all they're wanting you to do is evaluate your derivative for those given x and y values. So that's simply a matter of substituting in the x value, substituting in the y value. So you could actually leave it as negative 1 over the square root of 3. You do not need to rationalize that like you've had to in previous math classes. Now, if you wanted to, we would rationalize it by multiplying both the numerator and the denominator by the square root of 3. And so you would get negative square root of 3 over 3. So then for part B, where it says to find the equation of the tangent line to the graph of x squared plus y squared equals 4 at the point 1 comma square root of 3, the same rules still apply. To find an equation of a tangent line, we just need a point, which they've given us, and we need a slope. Well, we get the slope by evaluating the derivative at the point, which we just did in part A. So our slope would be our answer from part A. So our tangent line would be y minus y1 equals m times x minus x1. So you get y minus the square root of 3 equals negative square root of 3 over 3 times x minus 1. All right, and then part C says, at which point on the graph of x squared plus y squared equals 4 does the slope equal negative 1? So again, slope is the derivative. So they're basically saying, when does dy dx equal negative 1? Well, our equation for dy dx is negative x over y. So when does negative x over y equal negative 1? Well, if we try to kind of work with that a little bit, we can multiply the y over. So that would be negative x equals negative y, or x equals y. So the points are going to be whenever x and y are the same, whenever x is equal to y. So I want actual points, though. Like I want numbers for coordinate pairs. So I'm going to take this relationship and I'm going to put it into the equation for my function to find all the points on my function where x and y are the same. So I'm going to do that with some basic substitution. If x and y are the same, then instead of saying x squared plus y squared equals 4, we could replace that y with an x, or you could have replaced the x with a y. Either way, it would work. If we do that, though, then we only have a single variable to solve for. So x squared plus x squared would give me 2x squared equals 4. Divide by 2. And so x is going to be both positive and negative square root of 2. So since they wanted points, though, my answers are going to be x, y pairs. So I've got x is positive square root of 2, and I have x is negative square root of 2. I just have to find the y coordinate that goes with each of those. So that's where I go back to here, where I figured out the relationship between x and y. Notice x and y are the same. So if x is positive square root of 2, y is positive square root of 2. If x is negative square root of 2, y is negative square root of 2. This here is the graph of x squared plus y squared equals 4. It's this circle, centered at the origin with a radius of 2. And those two particular points happen to be right here and right here. And notice if you draw in those two tangent lines, they do have slopes of -1. Okay, so let's take a look at one more problem here. We want to find the derivative if 3y squared plus 2y is equal to 5x. So again, you're just going to go term by term through here. 3y squared, we could use the power rule on, and so that would become 6y to the first. But I just did a y derivative, so I need to write dy dx next to it. Then bring down my plus sign. 2y, the derivative of that is a 2. Even though the y has now disappeared, I still just did a y derivative. So I have to write dy dx there. Then I bring down my equal sign. The derivative of 5x is 5. That was already in terms of x, so I do not need to write dy dx next to it. Now notice here, I now have two dy dx terms. So I would bring them to the same side. These two happen to already be on the same side though. So now I want to factor dy dx out of those two terms. If you factor it out of this first term, you're left with 6y. And if you factor it out of the second term, you're left with plus 2. And then we still have our equals 5. So then the last thing you want to do is you want to isolate the dy dx by itself. So that would be 5 over 6y plus 2. And that would be your derivative for this problem.